The story so far. Everything can be described by an element of a Hilbert space. When you make measurements on systems, then they collapse in a particular way given by the measurement postulate 2 there, and they evolve over time according to Schrodinger's equation, which is entirely linear. Because it's linear, we discovered that we could describe the evolution by a single operator, which happened to have the unitary property, and we could either break up our evolution to be entirely associated with the states or the operators, or a bit of both, being the Schrodinger, Heisenberg, and interaction pictures respectively. And once we have this idea of unitary operators describing our evolution, we also noted that unitary operators also describe continuous transformations. And indeed, an arbitrary evolution is some kind of continuous transformation. And from that, we rediscovered Noether's theorem, the fact that a symmetry, the Hamiltonian, implies that the generator of that symmetry is conserved. And the classic example we had of that, and have seen a couple of times, is that if we translate our system for a translationally invariant Hamiltonian, then momentum is conserved because the generator of translations is momentum. So we worked out the form of the translation operator. The translation transformation, if you start off with a state, and we'll do it in 3 dimensions now. So that vector notation means it's code for 3 variables. So we're going to do a translation. We're going to translate by a 3 vector R. So that acting on our state has to move this. And so what it does is take everything from one vector to the appropriate translated vector. And we also know that the generator of translations is momentum, so we also know this. So we know it's of exponential form because translations are additive. And note that the momentum here is the only operator. These are just numbers. These are not the position operators. This is just the number, the amount that we're translating by. But this generator here, this momentum, is our momentum operator. Now you might recall when you first learned quantum mechanics that the momentum operator had a particular form in the position basis, and that might have come out of roughly nowhere. But what we can do here is we can actually demonstrate exactly what that operator should be, because we know exactly what the translation transformation looks like in terms of the momentum operator and in terms of the position basis, so we can put the momentum operator into the position basis. So ultimately all we're going to do here is we're going to apply the translation operator to both sides. On the left-hand side, we'll have the exponential. On the other side, we'll be applying this to that and get, there we go. Now we're going to expand this into orders of R. Now how do we expand this in terms of orders of R? Well, it's easy to do the Taylor expansion. We get the value at x and then minus R times the derivative. And because we've got 3 dimensions here, it's the gradient evaluated at x. And of course we have terms of order r squared with second order derivatives and so forth. Now this is true for all r. And so it's true for all orders. The 0th order is simply that the state is equal to the state, so that's easy. So the first order version is this. There we go. And again, this is true for all r. And so therefore each component of it must be individually correct. And so we have that if you apply the momentum operator to the state, multiply both sides by I h bar, then you get this, which is essentially the relationship that you learned when you first learned about the momentum operator in quantum mechanics. That if you apply it to the state, then that's like taking minus I h bar times the gradient of the wave function. Here we've left in all the Dirac notation to make it very clear that you can't write that the momentum operator equals minus I h bar gradient, because the mathematical objects there are not quite the same. This acts on kets and this acts on functions. So there's certainly a relationship here. So if we get rid of the equals, we can replace it with a sort of correspondence, but that's the exact equality there. So that's the momentum operator in the position basis. Of course, the position basis was a very difficult basis to try and understand the momentum operator. An operator is best understood in terms of its own eigenstate. So if I have a momentum operator and I have a momentum eigenstate, then by definition, that's an eigenstate, and the eigenvalue we will call momentum. So one of the things I like about this equation is that it uses P in 3 completely different senses: as the operator, as the index of an eigenstate, and as the eigenvalue of that eigenstate. So this is basically the definition of these states P, if you will. Now putting the momentum operator into the momentum basis, that's showing what it does to a state in the position basis. Putting it into the momentum basis is very, very easy. We simply pre-multiply it by the identity and post-multiply it by the identity. And using the completeness relation we used before, we can expand these identities in terms of any complete basis, and the momentum eigenstates are an excellent basis to choose. I guess all of these should be vector valued. There we go. Momentum operator. And now, finally, we can't use the same dummy variable, so I'll use p dash. A nice thing is that the momentum operator acting on this just brings out a p dash. So we get a p dash. And then we'll have the inner product of this p vector and this p dash vector, which is going to be a Dirac delta function. And then we'll have this ket and this bra left over. But then, of course, we can perform the integral because we've got a delta function, and that makes it very easy to do integrals. So we'll end up with one less. And all the p dashes will turn into p's. So a very simple way of writing out the momentum operator is that it is exactly diagonal in the momentum basis. And the momentum basis was always going to be an easy way to write the momentum operator.